Hello, my name is Philgu of Seoul National University, and the title of my paper is Automated Inspection Methodology of Wall Rebar Spacing and Diameters Using Laser Scanning. Rebar inspection is a vital task on construction site. The load-bearing capacity of reinforced concrete structure is dictated by size and quantity of rebars, which is specified in the design drawings. But if the rebars are not enough for missing, the structure is at risk of catastrophic failure, so strict combat checking is essential. However, the prevailing practice of rebar inspection is still a manual tape measure survey. This method is slow, labor intensive, and exposes inspectors to a safety hazard. To overcome these shortcomings, previous researches has turned to laser scanning-based inspection. The laser scanners can require high-quality data, require no physical contact, and support 3D modeling as well as quantitative analysis. Leveraging these capabilities, previous researches focus on automatically recognizing rebars and predicting their diameter and spacing. However, there are some limitations. Most prior research were conducted under controlled laboratory settings and predominantly dealt with rebars larger than 10 millimeter. But construction environments are far more complex and varied that there are so many congested reinforcement, rebars can be bent, and also the scanner placement is often restricted. Such conditions can make recognition of rebar and predicting their diameter and spacing difficult. For this reason, the goal of this study is to develop the methodology that automatically inspect reinforcement on construction site. To achieve this, we will detect rebar by using laser scan data and automatically predict diameter and spacing. The research framework is as follows. First, we generate the 3D point cloud, and individual rebars are segmented according to their arrangement characteristics. On this basis, we predict bus diameter and spacing. A structure is a building under construction, and object of interest is a double-layer reinforced wall rebar. Most of rebar size were 10 millimeter diameter. We used forward-focused laser scanner, acquiring 5 scan locations, and scan time was roughly 5 minutes for each. We generate the point cloud, and to limit the computation cost, we applied 5 millimeter pixel downsampling and statistical outlier removal. To extract the rebars, we split their linear geometry. For each point, we calculate the radius nearest neighbor covariance within a 5 centimeter radius, perform eigenvalue analysis, and derive a linearity index like that. Because the rebar is straight, so it shows high linearity, whereas formwork and noise do not. By keeping only points with the linearity above 0.3, we can remove most clutter. But there are several reinforcement directions, so we should split the point cloud by plane. By using 3D RANSAC iteratively, we can fit one plane after another and align the points to their closest plane. And one plane has 2 layers, so to split them, we calculate the distance between every point to their fitted plane and apply corner density estimation to generate the continuous density histogram and also locate the 2 dominant peaks in the middle illustration. And the points near peaks are then grouped into respective planes, like right in illustrations. And we run a RANSAC-based line fitting to fit one rebar after another. And this method makes no prior assumption about orientation. It makes robust even when some rebars are slightly bent. And we use PCA, principal component analysis, to calculate the arrangement axis, and we split the horizontal and vertical rebar. For diameter prediction, we use the concept of shape of cross-section data of rebar. Because when we look at the rebar from the measurement axis, we can see the point cloud as a circle because laser scanner can capture the rebar on the surface. So we project all of point cloud onto cross-section plane and fit the RANSAC circle fitting. But before that, we slice the rebar segment into 30 centimeter intervals because when we project all of rebar, there are so many noise and curvature, so everything is overlapped. So we slice each rebar and estimate the diameter. Each slice diameter is categorized into closest nominal diameters from D4 to D19. And most frequent value among all slices is taken as the final diameter. And for spacing prediction, we use also horizontal and vertical axis. All point cloud and compute centroid of rebars are projected onto vertical axis and horizontal axis. So we can compute the center to center distance between neighboring rebars. So the sequential result is as follows in right illustration. So this is the rebar results. So for total rebar, we get precision of 82%, we call 97%, and this identifies that my algorithm predict true rebars in high chance. And these are the diameter precision results. All of ground truth diameter was 10 millimeter. So in rebar level, we predict the ground truth about 54% and mean absolute error of 2.4 millimeter. In the illustration, the yellow line represents the correctly predicted cases. And in the spacing precision result, we compared with the manually measured value. So the MAE was 6 millimeter and accuracy shows 98%, which predicted very high. But when we see the cross-section data in diameter prediction, we assume that it appears as a circle, but when we see some of the example, it is not looks like a circle. So it is difficult to visually validate my algorithm. But by contrast, in spacing prediction, high density point clouds align precisely with computed rebar centroids. So this demonstrating my algorithm is reliable. To summarize this, we apply the novel approach for rebar detection, which is applicable to construction sites, even when the rebars have complex shapes or are bent. And also we established the automated inspection for rebar diameter and spacing. And there are some limitations because we only test the construction site with 10 millimeter diameter, so we should extend it to other sides of rebar. And this is my references. And thank you for listening.